Hello, good day. Today we are going to discuss the stress distribution in soils due to point loads. Estimation of vertical stresses at any point in a soil mass due to external vertical loadings are of great significance in the prediction of settlements, of buildings, and in any other structures. And according to the elastic theory, constant ratios exist between stresses and strains. And for the theory to be applicable, the real requirement is not that the material necessarily be elastic, but there must be constant ratios between stresses and the corresponding strains. So therefore, in non-elastic soil masses, the elastic theory may be assumed to hold so long as the stresses induced in the soil mass are relatively small. So we have here this first method or formula for calculating point loads. So we have this Boussinesq formula for point loads. So as you can see in the figure, a load Q acting on point O on the surface of a semi-infinite solid. A semi-infinite solid is the one bounded on one side by a horizontal surface, here the surface of the earth, okay, and infinite in all other directions. The problem of determining stresses at any point P at a depth z as a result of a surface point load was solved by Boussinesq in 1885 on the following assumptions. So first, we have to assume the soil mass is elastic, isotropic, homogeneous, and semi-infinite. Okay? So the soil is said to be isotropic if there are identical elastic properties throughout the mass and in every direction through any point of it, and the soil is said to be homogeneous if there are identical elastic properties at every point of the mass in identical directions. And we have now the semi-infinite because we don't know the exact or the actual length, because sometimes this length varies. So in our further discussions, you may understand how is this being called a semi-infinite. And the second is the soil is wetless. And third, the load is a point load acting on the surface here. So as you can see, this is now our point P. And then we are going to determine the vertical stress denoted by the sigma subscript z at a radial distance r from this vertical axis, no, from of this point load or concentrated load Q acting at point O. Okay. So in order for us to get this distance from point O to this point P, so we need to take now the square root of the squared of the sum of our Z and R. Okay? So proceeding, we have now this formula of the vertical stress sigma Z, okay? Which is equal now to the product of our 3Q over 2 pi Z squared times this quantity 1 over 1 plus the ratio of R over Z squared and raised now to the exponent of 5 halves. So, as you can see here, we let our I subscript B, which is the influence factor here, is equal now to this 3 over 2 pi times this quantity 1 over 1 plus the ratio of R over Z squared raised to the 5 halves from this formula here. So, if we assign this 1 and this 3 over 2 pi just equal now to I subscript B or the influence factor, so we can say that our sigma G just reduces now to this equation, which is equal now to Q over Z squared times the I subscript B, which is our influence factor. So here the R is the horizontal distance between an arbitrary point P below the surface and the vertical axis through the point load Q, and Z is the vertical depth of the point P from the surface. And we have to take note of this one. This influence factor I subscript B has a maximum value of 0.48 at R over Z is equal to 0, indicating that the stress is a maximum below the point load. Okay? So second, we have now this Westergaard's formula for point loads. And its formula denoted by this sigma z is just equal now to this q over 2 pi z squared times this quantity. Okay? So there's a presence of mu here. Okay? So this mu is our Poisson's ratio and mu is taken as 0 for all practical purposes in our lecture here. Okay, so if we are going to substitute this mu, it just equal now to 0. So this vertical stress sigma g just reduces now to this formula q over the pi z squared times this quantity 1 over 1 plus 2 times the ratio of r over z squared and raised now to the power of 3 halves. Okay, so we have here an assigning of our I subscript w, which is now our influence factor. As you can see, this 1 over pi over this 1 plus 2 times this r over z squared raised to the 3 halves. If we assign this one here, as we assign this one here, so this will reduce now to this formula for our vertical stress, which is equal now to this q over z squared times this I subscript w. So the I subscript w has a value of 0.32 at r over z equal to 0, which is less than that of this I sub b by 33%. So here in this figure 2, which is the values of our I sub b and I sub w. So here is now the at depth, at a certain depth and a radial distance. So we have this ratio of r over z. If our ratio of r over z is equal to 0, so most probably our I sub w is about 0.32 here, okay? And for the our I sub b, so more or less if we have this ratio of r over z equal to 0, so this is just equal now to 0.48 as discussed in our previous slide. So actually we can use this graph no to determine the values no of our I sub w and I sub b. And geotechnical engineers prefer to use Boussinesq solution as this gives conservative results based on this graph. Okay. So to understand fully the two methods no, of calculating the point load, so we have here a simple problem number one. So here, a concentrated load of 1000 kilonewton is applied at the ground surface. And we are going to compute the vertical pressure or the vertical stress first at a depth of 4 meters below the load, and second at a distance of 3 meters at the same depth. And we are going to use the Boussinesq and Westergaard's equations for this problem. Okay? For solution here, we have to use first the Boussinesq. Okay? First is this one. Boussinesq equation. Or we just call it formula. And then after this Boussinesq, we are going to use the Westergaard's. Okay? So based on the problem, at a depth of 4 meters below the load. So actually, if you have now this simple drawing, no, to illustrate better on this one. So we have here, we'll just have to draw a line here. Okay. So we have also here the load. Okay. So if we're going to have this one, okay, so this would be now our Earth surface here. Okay, so we are going now to draw the load P. Okay, so this would be now our, in this case, our load Q, point load Q. Okay, and this would be now our point O. So this Q is just equal now to 1000 kilonewton. Okay, and at a depth here 4 meters below the load. So if we have now this depth, okay, so example, this is now our depth. Okay, so we have here depth. We assign this one as 1. Okay, so at point, a certain point here, okay, so we just take this one as our point 4. Okay, so we have this depth of from O to point 4. We have a depth here equal now to 4 meters. Okay, so we will have here 4 meters, and this would be now our point here. Okay, at this one, okay, so we have this depth of from the soil surface up to this point, which is 4 meters. Okay, so actually here from this one, our R is just simply equal now to 0. Okay, because this point acts no directly below the point O, and we have also our Z here equal now to 4 meters. Okay, so by Boussinesq formula, based on this one, so we have now this value of, or this formula rather, for our vertical stress. So it is being denoted by this sigma subscript Z is equal now to this point load Q over our depth squared times this influence factor of IB. Okay, so we need to determine no this IB, in which our influence factor IB is just equal now to 3 over 2 pi times this quantity. Okay, so we have now this 1 over 1 plus this r over z, ratio of r over z squared, and then we are going to raise this one into 5 halves. Okay, so since our r over z is just equal now to 0 over 4, so r over z is just equal now to 0. So if we are going to substitute here, so our I over b is just equal now to this 3 over 2 pi times here. Okay, so we have now this quantity 1 plus this would be now 0 squared raised now to the 5 halves. Okay, and this is 1 here. So this would be now equal to just equal to 3 over 2 pi. Okay, so this is just 1 raised to the 5 sub, so this quantity will be equal now to 1. So this will just equal to 3 over 2 pi. Okay, so we have now this value of our influence factor IB. Okay, so calculating now the sigma subscript z, or the vertical stress, so we can say that this point load q over z squared times your IB is just equal now to, here our q is 1000 over our z is 4 squared times this influence factor IB, which is 3 over 2 pi. So if you are going to calculate this one, our vertical stress is just equal now to 30 kilo Pascal. Okay, so this would be it now for our Boussinesq formula for the vertical stress, no, for this 4 meters, no, this point acting 4 meters below the point O. Okay, so second, we are going to determine the sigma z using the Westergaard formula. Okay, so we have here this Westergaard formula. Okay, so if you can remember, for our Westergaard formula, we actually have this formula. Our sigma z is just equal now to q using the influence factor. Rather, we are going to use the I subscript w in this case, no? So we have here q over z squared times our I subscript w, or our influence factor. So where our I subscript w is just equal now to So here we have to write first, no? The denominator here. So 1 plus 2 times this ratio of r over z and raised to the squared and to the exponent of 3 halves. Okay, and here in the numerator is 1 over 5. So this will be now our I subscript W. So this R subscript R over the Z. Rather, this ratio is just equal now to 0. So we can say that when you are going to substitute, so this I subscript W is just equal to 1 over pi. Okay, so this was 0, so this will remain 1 raised to the 3 halves is just 1, so therefore 1 over pi. So we are going to determine now the vertical stress Z, which is equal now to this Q, which is 1000 over Z squared times 4 squared times this quantity 1 over pi. Okay, so our sigma Z here is just equal now to 19.89 kilo Pascal. Okay, so as you can see, for Boussinesq, we have 30 kilopascal, no, for our vertical stress. But for the Westergaard solution or equation, we have this only 19.89 kilopascal. So this will justify that for practical purposes, some geotechnical engineers will just use this Boussinesq formula because this is conservative, no, in terms of the vertical stress compared now to the Westergaard. So we are done with this first, no, at a depth of 4 meters below the load. So second, we are going to determine the vertical stress, no, at a distance 3 meters at the same depth, meaning our 3 meters here is just our radial distance or our R. Okay, so we have here our second one. So again, using the Boussinesq formula, so again, we have this additional parameter which is our R, which is equal now to 3. So in this case, we have now this R, which is equal now to 3 meters, and our Z is just the same, which is equal now to 4 meters. Okay, so our R over Z is just equal now to 3 over 4, which is only 0.75. Okay, so from our formula, we can directly substitute this one, no, for our I sub B, okay, which is equal now to this 3 over 2 pi here, and then we have in the denominator here is 1 plus 0.75. This is squared and raised now to the power of 5 halves. Okay, so if you're going to calculate this one, so this is just equal now to 0.156. Okay, and then for our vertical stress sigma z is just equal now to our q, which is 1000, over the z squared, which is 4, 4 squared here, times this 0.156. Okay, so we have now our value of z, which is equal now to 9.8 kilo Pascal. So we are done with this Boussinesq formula for the vertical stress, no, for this point P, and then we are going now to determine our sigma z using the Westergaard. So here we have now for the Westergaard's or the Westergaard formula. Okay, so we can directly substitute this one to our formula using the Westergaard. So our I subscript W is just equal now to, first we have now this 1 over pi here, and then in the denominator is we have now this 1 plus 2 times r over z squared, and we are going to raise this one to the power of 3 halves. So substituting here, so we have this 1 over pi, and then here 1 plus 2 times this ratio of 0.75. Okay, then squared and raised now to the power of 3 halves. So here we can get the value of our I subscript W, which is equal now to 0.103. Okay, and subsequently we are going to calculate now the sigma z, which is equal now to q. Our q is 1000 and our z is 4 squared times this 0.103. Okay, so we can have this value of our sigma z is equal now to only 6.4 kilo Pascal. Okay, so this would be it, no, for the Westergaard. So as you can notice also that this Westergaard is really below the quantity, no, of this Boussinesq formula. This is 9.8 and this is just only 6.4 kilopascal. So for this problem, this is just a very simple illustration on how to apply the Boussinesq and the Westergaard formula in calculating the vertical stress. Okay, so again we have now this another problem now for us to better understand the application of this Boussinesq and Westergaard formula. So problem number 2, a rectangular raft of size 30 by 12 meters founded at a depth of 2.5 meters below the ground surface is subjected to a uniform pressure of 150 kilopascal. Assume the center of the area is the origin of coordinates 0 and the corners have coordinates of this 6 and 15. So we are going to calculate stresses at a depth of 20 meters. So we have now this depth z, which is 20, and below the foundation level by methods of this Boussinesq and Westergaard at coordinates. So 0, 0, 0, 15, 60, 615, and this 1025. And we are going to neglect the effect of foundation depth on the stresses. Okay, so for our solution for this, we have now this simple, no? Uh, we will use and make a table for this so that we can input, no, the values of our ratio of R over Z, and subsequently, after getting this ratio, we are going now to determine the IB, which is our influence factor for Boussinesq and its corresponding vertical stress, and the same also for the Westergaard I subscript W and our sigma subscript Z. So as you can see, this one here is just a very simple, no, top view of our rough foundation, having this size of 30 by 12 meters. So here from this drawing, actually we have here this, since the problem says that the center of the area is the origin at coordinates 0 0 here. So we have now this 0 and this 0 here. This is now the center of our coordinates, no, of the rough foundation. So here to this point, as you can see, if you are going to this point, so its coordinate will be, since this is 12 meters here, according to the problem, this is 12 meters here, the width, and this length is just equal now to 30 meters. Okay, so actually, if this is 30 meters, so this would be 15 here, and this could be a distance here of 15, also here a distance of 15. Okay, and if this is 12 meters, so more or less this side to this side, to this point rather, is just equal now to 6 meters. Okay, also here equal now to 6. So if we are going to determine the coordinates, so at this point is 0 0. So if we get the coordinates here, so distance from here to here is just this 6. Okay, 6 meters. So that's why this is 6, and our y is 0. Okay, because our y here is 0, so only the this 6 meters, no, here for our x. Okay, so we have 6 0 here. So at this point here, so since this one is our origin, so this is 6 meters also here, our x, and our y is just equal now to this distance from here to here is equal now to 15. That's why this is 6 and 15. Also the same here, no, since they are symmetrical, so this is also 6 and 15. Okay, and from this point to here, so this would be now equal now to this 0 and 15, also here 0 and 15, while the other corners, since they are symmetrical, so 6 and 15 also. Okay, so based on this one, we have now this coordinates, no, of the rectangular rough foundation, but the problem said that there's a certain point there that we are going to calculate, no, the vertical stress at this point, which is outside the boundary of our rough foundation. So this is having a coordinates of 10 meters here, and our y is just equal now to 25 meters. So later we'll just consider first, no, the coordinates, no, this 0 0 here, and then this 6 0, this one, and this 0 15 here, and this 6 15 here. So the last one will be now this 10 and 25 at this point. Okay, so proceeding with this one, for our solution, we first consider the Boussinesq formula. Okay, so considering the Boussinesq formula. Okay, so we have here first we are going to determine actually the influence factor here. Since our basic formula for the vertical stress is sigma z is just equal now to this q over z squared times your influence factor I subscript b. Okay, so from here our I subscript b is just equal now to actually we have now this 3 over 2 pi, okay, times this 1. Okay, so its denominator is we have here 1 plus the ratio of our r over z squared raised now to the 5 halves. Okay, so this is really our formula. So from the given, so if we are going to consider now the coordinate, okay, we have now this a point 1 at coordinates, no, our coordinate here is 0 and 0, so therefore we can say that this is now our coordinate here. Okay, so therefore our r here is just equal now to 0. Why? Because this is not the center of our rough foundation and there's no radial distance, no, because the load is acting directly above this 0 and 0 coordinates. Okay, so our r is just equal now to 0, and then our z based on the problem is just equal now to our z is the depth, no, the depth of that one is below the foundation, so it is 20 meters. Okay, so we can say that our r over z is just 0 over 20. Okay, which is just equal now to 0. Okay, so here our r over z is just equal now to 0. And then we are going to calculate now the influence factor, no, I sub b. So we will use this formula. So our I sub b then is just equal now to, so if this is 0, so this is 1 raised to the 5 halves, still 1. So this would be 3 over 2 halves, no? Or in decimal, this is just equal now to 3 over 2 halves, which is equivalent now to 0.48. Okay, so we have now this value of 0.48 here. Okay, so we can say that our sigma z is just equal now to our q over the z squared times this ib. Okay, and we already have now this influence factor b, I sub b equal now to 0.48, and we also have now this z which is 20 meters, but we don't have this yet, this q. Okay, so this q is we still need to determine, but then based on the given problem we have this value of our q. Okay, this is small q. So from the problem we have now this pressure, no, of this uh, rough foundation, which is equal now to a uniform pressure of 150 kilo Pascal. So Based on formula, pressure is just equal now to the load. Okay, our pressure is just equal now to the load Q over the area. Okay, in which in this case the area is, we have now this Q over, our area is just simply the times this length, the width and the length. Okay, so our Q is 150, so we can say that 150 is just equal now to our Q over the area of, we have now this width of 12 meters times this length of 30 meters. Okay, so we can actually get the value of our Q, which is 150 times 12 times 30, which is just equal now to 54,000 kilo Newton. So we have now this value of our Q. So therefore, we can calculate now this vertical stress actually. Okay. So calculating now the vertical stress here. So sigma z is just equal then to our Q, which is 54,000 over the z squared. Our z is just 20 meters times our value of the value of our IB, which is 0.48. Okay, so this is our IB. So our sigma z is just equal to 65 kilo Pascal. Okay, so we can therefore say that this sigma z here is just equal now to 65, okay, kilo Pascal. So we are done with the Boussinesq, and then we are going to proceed with the Westergaard. Okay, so take note our Q is just simply equal now to 54,000 kilonewton based on the given problem. Okay, so we are going to determine the I sub W and this vertical stress using the Westergaard. Okay, so here we are going now to use the Westergaard formula. Okay, so based on this one, we actually have the same vertical stress formula, no? But we are only dealing with I subscript W here as our influence factor. Okay, so we have here this sigma z is just equal now to still our Q over our z squared times we are only dealing with I subscript W. Okay, so where our I subscript W is just equal now to, if you can still remember this formula for I subscript W, which is 1 over pi over this quantity here, 1 plus 2 times the ratio of your R over Z squared raised now that one to the power of 3 halves. Okay, so since our R over Z here is just equal now to 0, so 0, so 1, so therefore our I subscript W is simply equal now to this 1 over pi. Okay, so simply this is just equivalent to 0.32. Okay, so here we are going to put it here as 0.32. Okay, so calculating now our vertical stress, which is equal now to this Q is 54,000. Okay, over this depth of 20 squared times our I subscript W, which is 0.32. So we can have a value here of about 43 kilo Pascal. So we have here this one as 43 kilo Pascal. So now we are done with the coordinates 0 and this 0. Okay, so we are going to proceed using this coordinate of 6 and 0, which is at this point 6 and 0. Also the stress that we are calculating here is just the same as to this point, having the same coordinates of this 6 and 0. Okay, so proceeding. So again, we are using the Boussinesq formula first, and then later we are going to use again the Westergaard. So we have here coordinates of 6 and 0, where our value of our r here is just equal to 6. Okay, 6 meters. And still our z is just equal now to 20 meters. So since this is now our origin, so the radial distance from here to here is 6. That is why our r is 6 meters. Also the same here is true for this coordinate 6, 0. A distance of 6 meters. Okay, so we have now this value of our r over z is just equal to 6 over 20. Okay, so which is equal now to 0.3. So we have here our value here at 0.3. Okay, so substituting for this I sub b here, since the formula for our influence factor for this Boussinesq formula is just equal now to this 3 over 2 pi times, we have now this 1 over 1 plus our r over z raised to the squared. Okay, and then this quantity raised now to the power of 5 halves. Okay, so substituting it here, we have now this I b is equal now to 3 over 2 pi times this 1 and 1 plus our r over z here is just 0.3 squared raised now to the exponent of 5 halves. So calculating here, our I sub b is just simply equal now to 0.39. Okay, so this would be now our I sub b here, which is 0.39. And calculating the vertical stress, sigma z is just equal now to 54,000. Then our z is 20. Okay, 20 squared times this 0.39. Okay, so we can actually get the value of our sigma z here equal now to about 53 kilopascal. Okay, so we have here equal now to 53 kilopascal. Okay, so we are done with our Boussinesq formula. So we are going to proceed with the second. Okay, the Westergaard. So we have here the Westergaard formula. So from here, we have this I subscript W, no? Since our vertical stress is just equal now to Q over Z squared times this I subscript W, where our I subscript W is just equal now to, this is just equal now to 1 over pi, okay? Then this quantity here, 1 plus 2 times R over Z raised to the power of 2 and to the exponent of 3 halves, okay? So substituting here the value of our R over Z, so our R over Z is just equal to this 0.3 actually. So we have now this value for this I subscript W, 1 over pi, and then we have now this 1 plus 2 times R over Z is 0.3 squared and raised now to the power of 3 halves. So we can have this value of I subscript W, which is equal now to 0.25. Okay, so we have here equal now to 0.25. Okay, and then we are going to calculate the vertical stress here. So sigma subscript Z, our Q is just equal again to 54,000 over the 20 squared times this I subscript W, the influence factor of 0.25. So our sigma Z here is just simply equal now to about 34 kilopascal. Okay, so therefore we can write it here as 34 kilopascal. Okay, so proceeding with this one, using the same formula, no, for the Boussinesq and this Westergaard formula, we can actually have this value of our R over Z, the Boussinesq IB, and the vertical stress, and the Westergaard's I sub W and sigma Z equal now to, using the same formula for the Boussinesq and this Westergaard, we have now here 0.75, and here our IB is 0.16. Okay, and we have now about here 22 kilopascal, and for the Westergaard we have here 0.1, and here we have about 14 kilopascal. Okay, and for this coordinate 6 and 15, we have here this ratio of R over Z, which is 0.81. Okay, and for IB is just equal now to 0.14, and here is just equal now to 19 kilo Pascal. Okay, and for our Westergaard, actually we have here 0.09. Okay, and here as 12 kilo Pascal. So proceeding with this one, 10 and 25 here. So we have here about 1.35, and for the Boussinesq I sub B is just equal now to 0.036, and we have here 5 kilo Pascal. Okay, and for the Westergaard we have here 0.03, and we have here about 4 kilo Pascal. So it's really the formula, no? The formula. Use the formula of the Boussinesq and the Westergaard, and then given the illustration I give you on how to use the formula and how to calculate now the corresponding I sub B and the vertical stress, and this I sub W and its vertical stress. So actually you can fill up now all of this data here in this table. So as of the moment, this could be it, no, for this day. And before we end, no, so I would like to have this video as for your reference, in which I also use the references, no, for this lecture by Morty and Budu, Tomlinson, and by Brahadas. So thank you very much, no, for watching, and please like, subscribe, and even share for more updated videos. And thank you very much once again for listening and watching, and God bless us all.